It is my pleasure to introduce Dylan Heuer from North Dakota State University, and he will be telling us about partial Permutohedra.
Yeah, thanks for the introduction and thanks for letting me give a brief talk here. Um, Fair warning, as we probably know, I'm just going to kind of be flying through a bunch of slides and a bunch of stuff. So um, it's probably going to go way too fast to fully comprehend a lot of things, but I'll just try to get as much information out there as I can. So I'm going to start with a little bit of uh, background, I guess. I would classify myself as not really a polytope person. So I started looking at like the objects that form vertices first, and then we said, why not just make a polytope out of them and see what we can find. So if I miss some obvious polytope things, I apologize. So for a little bit of background, uh, I started looking at some sort of generalizations of permutation matrices, which you could sort of think as, I guess, rook placements if you like that uh, definition better. But these are going to be matrices with entries that are 0 or 1, and at most 1, 1 in each row or column. And so you can think, if you know permutation matrices, these are just sort of rectangular analogs that allow for rows or columns to have no ones in them as well. And we can get a one-line notation in a similar way that we can with regular permutations, just by recording the position of the 1 in every single row. So if I look in this example, I have in row 1 a 1 in position 4, and I just keep going in row 2 a 1 in position 2, and then there's no 1s in row 3, so I record a 0, and in the fourth row there's a 1 in position 3, so I get this one-line notation 4203. And sort of in the normal permutation land, I'd be remiss if I didn't mention the generalization that is alternating sign matrices, which allows for negative ones to be included as well. And so we sort of have a partial analog of that I'm not really going to get into in this talk, but that's sort of the motivation why I first started looking at these things. So in this one-line representation, you can think of these permutations as words of length m with entries in 0 up to n, and then of course the non-zero entries have to be distinct since we're only allowing at most one in every row or column. So I just wrote some of the really small, easy to write out examples here, and we'll sort of see those come up again in a little bit. All right, so for the partial alternating sign matrix case, I said I wasn't going to get too much into this, but I just want to give a quick definition. We're basically going to allow negative ones to appear now in certain cases. So now we're going to say that if we look at it from the left or from the top, oops, I always have to see a positive 1 first, and then after that, I'm allowed to see like a negative 1 and alternate back and forth. And this is a little different than the normal alternating sign matrix case in that we allow the row and column sums to sort of end at 0, so we don't have to kind of sandwich all the negative ones with a positive 1. And we're also allowing the rectangular matrices, even though the one I wrote here was a square. And sort of independent of the polytope stuff, there's a lot of cool bijection and stuff you can do with alternating sign matrices, and we can do a lot of those things as well in this sort of partial alternating sign matrix case. And I had some pictures from a different talk, so I just threw them in here. So I had some pretty pictures. Right, so some important or interesting polytopes that we may already know a lot about would be stuff like the Birkhoff polytope. So this is the convex hull of like regular old permutation matrices. And then you could think of the the Permutohedra as the convex hull of the one-line notations of those vertices, or like I think you think of it as like the one skeleton of the actual polytope. And then we have maybe a slightly less studied alternating sign matrix polytope, which is the convex hull of the alternating sign matrices. And sort of an interesting connection between all these things is that, well, of course, the Birkhoff polytope should probably be contained in the ASM polytope, and they both project to the Permutohedra by just multiplication by the vector 1, 2, up to n. So you take something in one of these two polytopes and multiply it by just a vector 1 through n, you'll end up somewhere in the Permutohedra. And that's going to actually hold in the a slight variation of that holds in the partial setting as well. So these are basically the exact same definitions as the regular case, except now we're allowing sort of the rectangular and sort of partial sum rows instead. So the partial permutation polytope is just the convex hull of those partial permutation matrices. And similarly with the partial alternating sign matrices, if you take the convex hull of those, you get a polytope. But we'll just call the partial alternating sign matrix polytope. It just gets to be kind of a mouthful, but both of those project to the case where you have the convex hull of the partial permutations in one line notation. And this is going to be sort of the guy I'm focusing on for this talk. And I guess what I'm going to present is mostly just some maybe interesting or surprising connections I found just as I was looking through trying to figure out what is and isn't known about these polytopes, and maybe some connections to areas I didn't really expect to see. All right, so while we were just like studying these polytopes, we did sort of some normal polytope things. We tried to enumerate facets and characterize the face lattice and look at the volumes and stuff. So I just put some of the most nice looking formulas that we found or have conjectured to find here as just sort of a list of nice looking things that we can state as results. I'm not going to go into these results at all. I just want to claim that I have some. And then I want to look at some of the pictures of these partial Permutohedra. And so you can see fairly easily that the vertices are just going to be those one line notations that had like the maximal non-zero entries. So like in the m and n equals 2 case, these were all the partial permutations in one line notation, and we're not going to include these guys because the ones are not like the maximum that they could be. And so this is sort of the corresponding picture down here. The green one is p sub 2, 3, and you can kind of think of the green one sort of shrinks down towards the origin to give you the blue one, and the blue one shrinks down towards the origin to give you the red one. And that seems to be the case. So I don't know if that's like a cool thing or something that happens a lot with polytopes, but you can kind of see in this 3D picture I got from Sage, the same sort of thing is happening. The green thing is shrinking to the blue thing, and the blue thing is shrinking to the red thing. So those are just, the only dimensions we can actually draw. And now I'm going to take a sharp left turn to try to land in the spot where I didn't expect to be when I was looking at these polytopes. So let's do sort of a full reset and look at graphs. And you can kind of think of a tube of a graph to be sort of a subgraph of the graph that's a connected subgraph, I guess. So think of like, I guess this little grouping of vertices is a tube. And there's sort of three kind of special ways that tubes can interact on a graph. They can either be nested, so over here one of them is completely contained in the other, or they could be intersecting, so they share some parts, but one is not completely contained, so they sort of intersect, in this case just at one vertex. And they're called adjacent if they don't intersect, but if you union them, you'd get another valid tubing. So I forgot to write the word adjacent over here, but these guys are adjacent because if I union them, I get this group of 4, which is still a connected subgraph. And so if we consider sort of the tubes that we want for whatever reason, we're going to allow nested but not intersecting or adjacent. And so we call tubes compatible if they sort of are this, they could be nested, but they're not going to intersect or be adjacent. And a tubing is a set of tubes such that every pair is compatible. So here's a quick example of a tubing. We're allowing this nested stuff over here. We don't have any intersections, and then these guys are not adjacent because if I try to union them, it wouldn't be a tube because it won't be connected. Right, so why on earth are we looking at these tubes of graphs? Well, it turns out after this slide, because I forgot about it, The graph I'm going to be focusing on is the star graph. So this is just the complete bipartite graph with one vertex on one side and then M on the other. So here's sort of M vertices, and I'll just draw it like this so it looks more like a star. And then I'll just label the sort of lone vertex with an asterisk and just label the other ones with the numbers 1 through M. And so why are we caring about these tubes? Well, it turns out for any graph G, you can define its graph icosahedron to be a polytope whose face lattice is isomorphic to these set of tubings that have some order, which we don't really need to get into for this sort of short talk. And through a bunch of digging through papers and literature, I found out that it turns out that what I was looking at is sort of the partial permutahedron when M and N were equal is actually a realization of this graph icosahedron of the star graph. And I found this is sometimes called the stellahedron, which I guess makes sense because it's on the star graph. And so what this ends up giving us is sort of a different way to view at least some of the polytopes we're looking at. And in particular, while we were enumerating faces and stuff, just using Sage to try to find some nice formulas, when we were looking at this case when M and N were equal in the partial permutahedron case, we noticed that the total number of faces when we plug that into the OEIS was the number of chains in the Boolean lattice. And so this, as a combinatorialist, you hope that there's a good reason for this. And it was kind of hard to nail down a bijection just looking at it sort of from the matrix case, but it turns out to not be so hard from the graph and like tubing's point of view. So I won't get too much into this bijection, but I put an example here of how we can get from a tubing to a chain in the Boolean lattice. It goes through this sort of secondary thing sometimes called a spine, which is if you take the tubing, you're just going to order the tubes by inclusion. And then just to make things a little bit easier, instead of labeling every tube with all of the vertices in it, you sort of just label it with the new ones that weren't contained in a previous tube. So here I had my smallest tube just had the vertex 2, and then my next smallest tube had 2 and star, so I labeled it with star, and then this next biggest tube, or next smallest tube, had 1 and 4 added to it, and then we sort of consider the whole graph to be an ambient big tube that whatever was left over goes at the top. And you get the chain in the Boolean lattice by looking at starting with sort of the star level, recording all of the vertices that are in there. So there's nothing with star. So we have the empty set. And then as we go up, we get 1 and 4, and then we add 3 to that over here. And so we sort of just forget about everything that ends up below star. And so if we have this bijection between these tubings of the star graphs and chains in the Boolean lattice, through the sort of mysterious connection I never really nailed down in this talk about how this is actually a realization, or how the partial permutahedron is a realization, we can sort of characterize the face lattice of the partial permutahedron to be like through the relation to tubings to be viewed in terms of chains in the Boolean lattice, which I would argue are maybe a little more familiar combinatorial objects. And so we can get sort of k-dimensional faces lining up with chains with k missing ranks, which I won't really get into what that means. And then it looks like a very similar case with sort of this sort of weird added condition seems to hold when m is not equal to n. The reason this is maybe not as easy to just state right away as a proven theorem is because when m is not equal to n, this is no longer has like the direct relation to the graph icosahedra. And so I guess I haven't gone as carefully as I should have yet, just through the intricacies of the bijection to see if sort of this conjecture just holds as a theorem through the bijection. But what we won't be able to do without a lot of extra work would be to like actually say what is the relation within the face lattice, since we don't have the direct relation to the graph isosahedra. So even though we might be able to do some of the same bijections on the chains, we might have to do a little more work to actually show what the proper containment and stuff is. So yeah, I guess I've sort of rushed through it all in about 15 minutes. Sorry if that was just way too much information in a short amount of time, but this is sort of what I know so far about how these sort of matrix polytopes relate to what I didn't expect to see with these sort of graph isosahedra. So I have a bunch of references that I didn't want to write down, but I can certainly send them to you if you want.
That was a very nice talk. Let's thank Dylan. I think we have time for questions. So, Dylan, do you wanna meet yourself and ask it?
Yeah. So this shrink. So first of all, awesome conjecture. That's really cool. I hope it's true. Second of all, so this shrinking phenomenon that you noticed, I'm not a polytopes person. Maybe this is something that the polytopes people recognize. But if you were to take a special family of your partial permutations, like something like a 3-2-1 avoiding partial permutation, do you know if the shrinking phenomenon would still happen?
I don't know that. I don't know exactly how to, I guess I haven't thought that hard yet about how to like characterize pattern avoidance in partial permutations. I don't know enough about that, I don't think, to get into that, but that's a good question.
Is there any other question? I have one because I don't know, the pictures that you had in 3D are very nice, and it seems to me that what you're getting are type B generalized permutahedra. So have you looked at the edge directions that you get in these partial permutahedra?
No, because I don't really know what the right thing is to look at, I guess. As more of a, I guess I come from more the enumerative side of combinatorics. I don't know what the good things to look at in polytope blend are. So it'd be interesting to know what would be interesting questions to ask about these polytopes.
Okay, yeah, because so I think in one of your pictures, the face that you could see from this side was like a hexagon, and that's the permutahedron.
Yeah.
And the other edge directions seem to be either parallel to those or parallel to the axis, to the x-axis, y-axis, z-axis. And if you have something like that, that's a type B permutahedron. So maybe there's some hidden information that you could find if you study under that scope. So that would be maybe interesting to see.
Okay, cool. Yeah, I'll definitely look into that.
Are there any other questions for Dylan?
Jose, can I ask a question about your question?
Yeah.
Which is that if this is true that all of Dylan's polytopes are type B permutahedra, would that mean that these partial permutations are like somehow in bijection with signed permutations?
I don't know. That would be a great thing to check. That, yeah. I guess Dylan would know more about that. But what I was thinking about is that if it is type B generalized permutahedron, maybe there are nice formulas for the volumes or the other of these polytope invariants that might relate to some combinatorial invariants of the underlying partial permutations. So that could be something interesting. And I also thought about that because so you mentioned how in the case where M and N are equal, then you have some realization of a graph isosahedron. But in the other cases, you don't necessarily. I was thinking that maybe in other cases you get a type B graph isosahedron, which is something that I'm working on with my advisor. But I mean, as soon as we have something going around, I can send you that, Dylan. Maybe you can check if that matches your description of the polytope. That would be very good, very interesting.
Cool.
Okay, yeah, if we have no more questions, let's thank Diane once more.